Dunk. Okay. Length contraction. So we know from kinematics the relationships between time, distance, velocity. There's classical physics and there's relativistic physics. For a distance of some object, we call it length. And again, we're not really figuring anything out here. I'm not demonstrating how it works, but it's observed to be true. Special theory of relativity applying to a length, which again is a distance, right? It's just another way to say some one-dimensional measurement. The length of an object is measured to be shorter when it is moving relative to the observer than when it's not moving. How do we say that? When it is at rest. Okay? So just like time changes depending on what frame of reference you're in, so does any object. Its length changes. And I know in the picture it showed you that it changed in both dimensions. Now I'm not going to say I'm a PhD in relativity and physics, but from what I've learned, it doesn't move in a direction 90 degrees to where it's traveling. It's just the direction in which it's traveling. So this will shorten. Okay, the faster you go, the shorter it will be. But as far as this dimension, again, don't quote me, but we're going to go with the fact that its height doesn't change. Okay, just its width. All right? So we're just telling you that. Here's the formula. Looks a lot like the time one, only a little bit different, but at least we're consistent. So remember with our time dilation formula, which one was TO? This was which time? The guy in the spaceship or the person on Earth? The guy on the ship. So same thing. LO is, now I'm going to say the normal length. Meaning if this object is in the spaceship with this guy traveling, he's just going to see the same thing, right? Because according to him, he's not moving at all. It's everything else that's moving. So, for example, if I got a meter stick and I take it with me on my spaceship and travel near the speed of light, according to me, this thing's still a meter stick. But somebody on Earth watching this thing go by, it's not a meter anymore. It's a lot shorter. Okay? So LO, according to the spaceship, that's the normal length as observed by the person in the spaceship. L, just like T, it's according to, when I say the fixed observer, the person at rest, the person not moving. It's the length seen by, well, let's use the word fixed. Fixed person, or the observer on Earth. And it doesn't have to be Earth, it could be the moon, could be anywhere where he's not moving. And then again, he actually is moving, right? Okay, let's not go there. So, example, there's our formula. Got to know how to use it. There's 3 variables there. Again, I'm actually going to do one where I'm going to solve for V here, okay? How long is a meter stick traveling at 0.995 times the speed of light appear to be? Well, according to you, on the spacecraft, it's a meter. The speed is 0.995 c squared over c squared. And that's how we want it, right? Like in the question yesterday that said 1.5 times 10 to the 8 it'll work if you put that in there. Okay, you square both of these. That'll work. But what was easier that some of you guys found out? Like, what's 1.5 times 10 to the 8 in terms of c? It's 0.5. It's half of 3, isn't it? So if I go 0.5 c squared over c squared, then I just have 0.5 squared, not 1.5 times 10 to the 8 squared. It's exactly the same number, but it's a little easier if you think of that, okay? So the c squareds cancel out. So I have 1 times that is just that. Okay, and what does that give us? Now, should L be shorter? Am I looking for something shorter here?
Yeah.
Yes, I am. Because of course, according to someone on Earth watching this ruler go by, it's got to be a lot shorter. Square root of 1 minus 0.995 squared. And what was the units? 1 meter. That's in meters. Or rounded, how many centimeters is that? 0.099, well, 7 makes that a 9. That is 10 centimeters, or 0.1 of a meter, right? So I don't know what the answer might be in, but when you see this meter stick flying by at 0.995 times the speed of light, it's only that big, okay? That's how much shorter it got. That's length contraction, right? Do they know why? Well, like I said in the beginning, it's kind of complicated explanation. I showed you a video. That's all we're going to say, okay? Another question. So I could have worded this a whole bunch of ways, but there's a train. It's 500 meters long. And if it moves fast enough, it will actually enter a 200-meter tunnel, and you will not see the front of it exit the tunnel until the back of it is actually hidden by the tunnel. Okay? So how does a 500-meter train fit in a 200-meter tunnel? Well, length contraction, yeah. Okay, so this super train, how fast does it have to be? If you're in the train, according to you, that's a pretty big train, isn't it? 1/2 kilometer long, right? So which one is that? Is that L or L0? L0 is the normal length, okay? This one I'm wording it kind of easily. That is L0. So this one must be L. So 200 is 500 times, where's your formula? Right there. I got to solve this thing for V. So if you didn't know how to do this on the sheet yesterday, pay attention. It's a little different than the time one, but it's basically the same procedure. What's the first thing you want to do? Do I have numbers on both sides of the equation? How about I just divide both sides by 100? Now I got 2/5. I still have numbers on both sides. Let's collect them. How do I get rid? I want to solve this for V, right? I want to get rid of everything except V. How do I get rid of this 5? Yeah, divide it away. So you can divide by 500, you get the same thing. So 2/5 is the square root 1 minus V squared over C squared. What's the next step? Yeah, I want to get rid of this ugly thing called a radical. Square both sides. Whatever you do to one side, do to the other side. And then I have 1 minus V squared over C squared is whatever number this is. Okay? Getting a little nicer. This is negative. I want it to be positive, so I'm going to chuck it over there. Okay? So that's what I got. And then, well, if I got this over here, I'm going to put that over there. So I got 1 minus 2 over 5 squared. Okay? So if v's in terms of c, though, like what happens with these c's? They cancel out. So I can just not even worry about that if v's in terms of c, right? So I can kind of ignore that. And then lastly, how do I get rid of this squared? The opposite thing I did here, right? Take the square root of both sides. So that is going to be your velocity in terms of c. The square root of 1 minus bracket 2 divided by 5 is 0.4 squared. That's 0.92 c. 92% of the speed of light. Okay? So I can't just, now just to let you know, I don't know how picky I'm going to be when I mark these tests, but what does that mean? What's the unit? 0.92 meters per second? Yeah, you got to have a c there. It doesn't really make any sense, right? That means 0.92 times the speed of light, which is 0.92 times 3 times 10 to the 8, which is some number. I don't care what it is, okay? So again, that's in terms of c. That's why I can just cancel this c squared thing out. I don't have to put 3 times 10 to the 8 squared here, right? That's in terms of c. Okay? So again, with time, I'm going to ask you to do that on the quiz.